So I'd like to invite now Mike Burshteyn, CEO and founder of CryptoMove, who worked with really a lot of people, Google, Uber, Microsoft, Amazon, and he will talk to us about stuff that are post-quantum, mainly.
Sure.
Okay.
Thank you.
You can find your stuff here?
Yep.
If you need next mic, we have it.
Okay. I think it'll be okay. Okay, hi everyone. I'm Mike, CEO and co-founder of CryptoMove. I have to admit, I don't have a math or computer science or physics background, but my co-founder, and CTO Boris, who's also my dad, does, and he would be here, but we don't let him out of the office because we don't have enough engineers. But what I want to talk about is really practical, is how do you bridge the challenge of quantum computers coming and the challenges around data security. And we have a startup, and one thing that startups have to do to survive is to find product market fit and to find use cases that are a pressing problem today, even though quantum computers may happen sometime in the future. And so that's what I want to talk about, and applying this concept of moving target defense, which is what we work on, to the post-quantum world. And with CryptoMove, we started out with two basic ideas. This is really why CryptoMove was created, was pretty much my dad was thinking about this tug of war that we've heard several times throughout the day of you get stronger and longer key lengths, better algorithms, faster computers, and it's a constant back and forth. And we know today already there are many attacks on data where they attempt to exfiltrate with the idea that in the future the data can be, turned into clear text. And the challenge is that the data at rest today, the methods leave it as an easy and stationary target. So, okay. Now the other interesting thing is this quantum computer revolution, which might happen 5 to 10 years or within the next 50 years, whenever it happens, the world we live in from a data infrastructure perspective will look completely different than it does today. In the sense the data is getting spread out. Different environments, different clouds, onto devices, with microservices. Yet the data protection mechanisms rely on treating the data as a centralized and stationary target. So what did we come up with is a technology called moving target data protection. It's basically a software-defined secure storage system. Whatever you put inside it with CryptoMove, we'll split it up and fragment it and shard it into different pieces, encrypt those pieces with any algorithm. It can plug and play different ones. And then the key innovation is we continuously move them around distributed nodes. And so the entropy is derived as a function of time. As time goes by, one piece moves to another place, it gets re-encrypted, it can mutate and change properties. And so regardless of, and this is getting later into the talk, regardless of how fast your computer is or how powerful it is, you have to get the ciphertext. And so we just try to make that more difficult. And I'm going to talk about, okay, how can you apply something like this to a post-quantum world, and how can you actually apply it to business where companies have to focus on shorter-term priorities. And I'll say when we started out a couple years ago when we were just a few people, and my job was to try to sell these things, and we went around to CISOs and we said we have a technology that can help you if encryption fails, we didn't get a lot of excitement. And that's because of some of these difficulty in terms of uncertainty. But what we were able to do, and which I'll get to, is we were able to find a use case for this technology that is an important problem today. And I think that as we approach post-quantum security, we'll have to do that across the stack. And some of our earliest adopters and customers are in the United States government and military. The basic idea of moving target defense is actually something that can be applied across the stack. There's, in fact, an Israeli company called Morphisec that does it at the application layer. It can also be done at the network layer. We do it at the storage layer. And there's been a little bit of research starting to happen on how it can be related to quantum. And the basic concept is you attempt to generate entropy and make the defensive infrastructure dynamic, changing, constantly morphing, so that over a period of time, it doesn't get easier to attack. And so if you think about the challenge today with security infrastructure, is our defense infrastructures get bigger, it's harder to find all the threats and detect them. And that time is an asymmetric advantage to adversaries. So how does this really apply to post-quantum? I think that one big challenge, which we heard today several times in a few different lenses, is it's hard to fund and prioritize the quantum, the transition to a post-quantum world today, because the computers don't exist. Or if they do exist, we don't necessarily know about them. Or if they exist, they're not to the extent that they can break all the encryption that we're using today in a practical way. And so that uncertainty makes it very difficult to commit priority and resources. There's also another challenge, which there's a lot of post-quantum encryption algorithm work being done, right, around NIST, lattice-based cryptography, but it's not so easy to actually develop it, test it, validate it, and then implement it in very complex infrastructures. And so you need a bridge, you need something else. And you can think about this graph in terms of what is the anticipated risk of a quantum computer, the likelihood, and the cost of implementation. This is why you have a really big challenge for startups that have technology in this area and for businesses that actually want to do something about it. First, there's the uncertainty of risk. If we think the risk is extremely high, then even if the implementation cost is high, go for it. Sure, let's go and do whatever it takes. But what if we think it's medium? What if we're not exactly sure? What if we graph it over a time horizon that lets us say, maybe I won't be in this job when it actually happens? Then it actually becomes harder to prioritize. The same thing with development costs. The development costs are actually quite unknown. It's very difficult to understand what it would cost to change a Fortune 10 bank's infrastructure from today's cryptographic methods to post-quantum. I can tell you right now that just from my personal experience in this industry, just the transition from on-premise data centers to the cloud and to things like microservices and Kubernetes are extremely costly and difficult and slow in many situations. And so that's where we need some kind of a bridge. And so that gets into moving target defense. And so this concept of moving target defense fundamentally boils down to attempting to flip the asymmetric advantage that attackers have today. Over time, a system that doesn't change, that's static, is easier to attack. If we, let's say, fragment some secret piece of paper, spread it out into every building in the university and hide it, kind of like the Afikomen on Pesach, eventually, if you give the adversary enough time, they will find it. You can increase the key length of your cryptography. Eventually, over time, there will be challenges there. The idea of moving target defense is to flip that asymmetry. And it can actually be quantified. So there's some fantastic papers. There have been a few ACM conference groups on moving target defense, attempting to use game theory and apply a risk-based model to say, if the defensive infrastructure does not change, and versus if it does change, and then actually isolate, what are we talking about? The network infrastructure, the storage infrastructure, the application layer. How does that change the game? And you can use Markov modeling to actually quantify that. And just like with anything else, moving target defense systems have to take into account the cost of implementation. So here, some of the ones around network moving target defense, for instance, are actually quite costly. Because if you're constantly rotating IP addresses and network address locations, it can be difficult to do business and to run an infrastructure. The interesting thing we found in CryptoMove, and this isn't biased at all, as you can see I copy-pasted our logo into this chart, is it's actually low cost of implementation. There's a lot of interesting resources, and this, if you go to our blog at CryptoMove, we've actually published the outline of this talk, where there's people attempting to quantify and understand moving target defense in different contexts. But how does it actually apply as a bridge to quantum specifically? And so here I'll get into a little bit of a story of our startup and how we started out with this crazy idea of we're here to, protect your data, and every question we got in the first year or so was, well, why isn't the current encryption methods we use good enough? And it's actually pretty hard to overcome that question when you're competing with thousands and thousands of security startups and funded by millions of dollars in venture capital funding. But we found something, and I'm going to talk about it. And so I think that one thing you can really do with moving target defense is treat it like a bridge. To say that here's a technology that today can increase the security of data or keys, and tomorrow can actually be part of a post-quantum future. And part of it is this idea of time as entropy, which we talked about before. So what did we find? So the problem that we found was around secrets and keys. And we were able to figure out that basically in cloud-based development and Kubernetes development, the traditional kind of HSMs, private key, security in a hardware box is difficult to scale. And many breaches were happening because developers have to use their API keys and authentication tokens at scale across multiple environments and teams. And it leads to common anti-patterns in organizations where, we'll just email them to each other or send them via Slack. And developers, software engineers, they have the best of intentions, but it's just difficult to manage at scale. And so what essentially we did at CryptoMove is we hid our post-quantum technology underneath this use case that is very pressing today. And this is how we're helping to kind of establish the bridge. And what I would think is other challenges in post-quantum, if you look at the research, the kind of long-term research to the applied research to the R&D and commercialization to actual selling in the market, it will all go through this same pathway that we are going through as a startup. And so we have essentially a secrets vault where people can put API keys and tokens into CryptoMove. We split them up, encrypt them, continuously move them around across nodes, and that's what we do. And it turns out that if someone's using Jenkins, if they're using Kubernetes, which they are today rapidly, they really need a solution to this problem. And you can see a lot of big tech companies like Palantir, Square, Pinterest have actually built their own solutions. They've developed their own in-house kind of secrets management tools. Amazon has as well as Microsoft. And so we saw that there was an opportunity here in the market. Now, over time, our vision, it goes back to that very first slide, which is that encryption is a constant tug of war, and we want to protect the ciphertext and make it harder to get it all, and even if you did, it wouldn't necessarily add up. And so we would like to apply our technology to other areas where there's current encryption methods that might not hold up in a post-quantum world. But we sound too crazy when we talk about that with people that are actually spending money and budget and buying tools, and so that's why we've put it into this secrets management product. So that's kind of our story of CryptoMove. I think that, and I want to show some demos, just to show you how it works, and obviously take questions. But in terms of what the next steps for MTD are and quantum is hard to know. In this 50-year time frame, maybe it's faster, maybe it's slower. There's going to be changes in infrastructure, changes in how we look at data, changes in communications, and everything. Who develops the first quantum computer, to Jai's point, is a huge game changer. Is it going to be Europe? Will it be in the United States, in China, in Latin America? Will affect how that all plays out. And basically, I think that it's important to, as scientists, researchers, academics, and people that are involved in commercializing technology to think about what are the problems today that we can solve with kind of futuristic technology. Otherwise, it won't really ever get off the ground. So to go into just a quick, to show you all what I'm talking about, so it's not just theoretical. Here's an example of post-quantum data security technology that doesn't rely on any new algorithm. Oh, hold on. Looks like gotta refresh. So this is kind of showing you CryptoMove and how it works in the back-end data store. Or not. Here we go. It doesn't like when I fast forward, so we'll just watch the whole thing. It's about 2 minutes. So here, what we did is we actually developed a prototype of a file system integration. So this could potentially replace like your BitLocker in the future. You can see in the secret folder the data that you put in, the file size goes to 0. And on that endpoint, we're splitting it up, encrypting and fragmenting it, and continuously moving around. And we made it transparent so that when you open it back up, it recombines. So the person that's using this doesn't know anything about a quantum threat to encryption or quantum computers. And this is kind of the lesson we had to learn the hard way, is that to put this types of technology into the market, it has to be transparent. Here on the left is the debugging log showing you the movement in the system. We have a piece of data that was split 100 ways, make 2 copies for redundancy, and move it about 28,800 times a day, which is once every few seconds. And what we do on the client side is we encrypt it all to AS256, we split it up, we create the encrypted logs, we distribute it out across a bunch of TCP IP servers, which can be in containers. We've actually even put them on embedded devices like drones, can be in the cloud. And this is what it looks like on the file system. So you have a bunch of these little encrypted fragments that are constantly changing, re-encrypting with cryptographic names. And if you're trying to gather them for your quantum computer, they're actually not there anymore by the time you pick it up. And so the way to attack it, obviously, is to freeze all the movement and get everything. But if it's hard to do that, if it's spread out wide enough and it's moving fast enough, that's not so easy. If you did get it open, it's still encrypted. And so that's basically the idea. And then we can bring it back with a distributed tracking system. It's not blockchain, but it has some similar concept where we use cryptographic hashing of the prior location. And here you can just see in the 10 seconds since the first file system snapshot till now, this is the comparison of one piece of data and the entropy, and it continues. And so the attacker will have a tough time there. So this is kind of the concept, and hopefully it was helpful. So thank you very much.
Thank you, Mike. Do you have any questions? Over there.
Yeah. It's a classic problem that you have a really strong safe with strong walls, but when I open it, someone's standing behind me and knocks me on the head. So we made a stronger safe, but you still need a multi-factor authentication system. You need to be able to connect the identity of the person accessing it to that system.
Mike?
Yeah.
Maybe you could stand by the mic.
Yeah. So this is just one piece of the puzzle, basically. You also need some kind of strong identity and authentication system. And the question was, what if I just pretend to be an authorized user, have some way to access the symmetric data key that gets the data back? And so that's part of it. We also, in our system, we have server keys. So on each server, there's another key that gets re-encrypted. So it's hard to just steal one key and get it. It's part of the system. But I can share more like on the math and architecture there. Thanks for the question.
Any other questions? Yeah, other side.
be somehow pursued. They can be infinite, right? Because if I have application that need to write the real data close to real time, and if it continuously changes, how would that work?
Yeah, so it has to be fast. And from a programmatic perspective, you can actually use REST APIs to access it and get it in and out when you want. In terms of performance, I think we have some benchmarks here, but CryptoMove is actually quite fast. It's developed on a proprietary new distributed programming language that my dad came up with called Hello. And the other counterintuitive thing is because we're splitting up the data into smaller fragments, as you approach larger file sizes and you can concurrently encrypt them, the I/O actually goes up relative to just encrypting a big file. But you're right, and you have to think about how far is it spread out, how fast is it moving. The network bandwidth will eventually be your biggest limiting factor.
Transaction operations.
We've done it, so we've done live streaming real-time video on essentially an embedded drone with CryptoMove, where you can fly it. So it's fast.